Hey guys, thanks for watching my videos. Today I will talk about the importance of a dimensionless number, which is called the Reynolds number. And based on this dimensionless number, I have constructed an axis, as you see here, along with the Reynolds number changes. It starts from 0. This is the case of 0 Reynolds number for a flow, and this is the infinity. And along this axis, I've shown different flow regimes such as the instability, the laminar flow, the turbulent flow, or the boundary layer theory. Both ends of this axis correspond to two important and well-known flows. The first, here near 0, or at low Reynolds numbers, the flow is called the creeping flow, or the Stokes flow, or the low Reynolds number flow, or the lubrication theory. All of these important cases are related to this region in this axis, the Reynolds axis. And also the flow is linear, and the governing equation, which can be used to compute the velocity and the pressure distributions, is the Bi-Harmonic Equation. This is the Bi-Harmonic operator, del 4. Del 4 is the Bi-Harmonic operator, and as you see, this is a linear partial differential equation. Similar to this flow region here, we have another important flow at the other end of the equation, which is related to the high Reynolds number. Reynolds number is the ratio of the inertia and the viscous forces. So here in this part, we have negligible inertia in comparison to the viscous forces. So here the viscous forces are dominant. But in contrast to this regime, or to the creeping flow, and the potential flow, or the infinite Reynolds number, viscous forces can be neglected, and only we are dealing with the inertia. So again, the potential flow is a linear flow, and the governing equation is the Laplace equation. Here, the Bi-Harmonic operator of the psi function is 0, but in potential flow, the Laplacian of the string function is 0. Again, we have two paradoxes and two celebrated laws at two ends of this axis. In the creeping flow regime, we have the Stokes paradox, and in potential flow, we have the D'Alembert paradox, or D'Alembert paradox. The Stokes paradox says that the two-dimensional flow in the creeping flow regime is impossible, or satisfying the boundary condition related to flow over bodies is impossible in Stokes two-dimensional Stokes flow. This is the Stokes paradox. The other mathematical statement of this paradox is that when you are going to satisfy the boundary conditions at infinity in two-dimensional flow over something, over bluff bodies, and logarithmic singularity appears during the process of derivation of the result. So it can be concluded that the two-dimensional paradox, the two-dimensional Stokes flow is impossible, external creeping flow. And the D'Alembert paradox here says that the drag force exerted on any arbitrary object placed in a potential flow is 0. Apparently, this is a paradox because we all know that the drag force exerted on different objects is not 0. So this is the D'Alembert paradox, which talks about the drag force. Here we are talking about the possibility of two-dimensional Stokes flows. But in the creeping flow, we have a Stokes law. The Stokes law says that the drag force exerted on a body in a place in a creeping flow is proportional, see the constant here, is proportional to the product of three parameters. The first one is the viscosity of the fluid, the second one is the velocity of the fluid, or the velocity of the object, and the third one is the length scale of the problem. Here we have the Kota's law, Coulthard's law says that the lift force exerted on for example, an airfoil or a rotating circular cylinder placed in a potential flow is equal to the product of the length scale of the problem and the density of the fluid, the velocity of the upstream flow, and the circulation which is needed to construct that flow in the potential flow regime. So the creeping flow is related to the low Reynolds number with negligible inertia. It's linear, and the governing equation is the Bi-Harmonic Equation. The Stokes paradox, we have the Stokes paradox and the Stokes Law in this regime. And at the other end, we have a potential flow with the D'Alembert paradox and Coulthard's law, and again the flow is linear. And the governing equation is the Laplace equation. At intermediate Reynolds number, about the middle of this axis, the flow is non-linear, of course, and we have to find some other tools to analyze the flow behavior in these regions. In the intermediate Reynolds number, we have three critical Reynolds number. The first critical number is the Reynolds at which the instabilities start to grow in the flow field. So this is the critical unstable flow. The second critical Reynolds number maybe is the Reynolds number above which the boundary layer theory can be used to analyze the behavior of the flow motion. The Reynolds number for the validity of the boundary layer theory is approximately about 1000. And the third critical Reynolds number corresponds to the transitional critical Reynolds number, which is after which we have the turbulent flow behavior, and less than that critical Reynolds number we have a laminar flow. So we can record many videos about the behavior of the flow in this transitional regime. But for example, for a flow in a pipe, in a circular pipe, this transitional Reynolds number is about 2000. And this critical transitional Reynolds number differs from a system to another one based on the geometries or the surface roughness. But what's important here in this video is that we have three critical Reynolds number here. First, we have a creeping flow. There is a region here which you cannot use. You are not allowed to use the boundary layer theory. So the only approach to solve the governing equations of the fluid is the computational fluid dynamics. Here you can use the analytical tools because you have a linear governing equation, but based on superposition. But here you have no other choices than the CFD. The CFD is the only choice. And after the Reynolds number above which the boundary layer theory can be applied, you can use the theoretical approaches presented by Prandtl to simplify the governing equations and to find some solutions to the boundary layer equations. So here we have the laminar boundary layer, and after the transition occurs, again we have the turbulent boundary layer. In order to predict the behavior of the fluid in the transitional regime, your only choice is the computational dynamic, fluid dynamics, or the direct numerical simulation techniques. So we have creeping flow, then instability starts to grow, or disturbances start to grow, or the flow becomes unstable. And then you can use the boundary layer theory here, and the transition occurs, and the complicated behavior of the turbulent flow gradually starts. And then you have the potential flow theory here. Again, the flow is linear, and you can use the analytical tools to solve the celebrated Laplace equation to find solutions to the potential flow.